Hi, today we're going to talk about molecular orbital theory. So you might be wondering why we need to learn about theories about molecular orbitals. Didn't we already learn about that with valence bond theory? And the answer is not really. Valence bond theory explains something about how molecules bond, and it's very good at explaining why we get the molecular shapes that we do, because it's really based on simple geometry. Molecular orbital theory explains why. It explains why valence bond theory works. It explains why we end up with double bonds or triple bonds or single bonds in a particular molecule. And it explains why some molecules are magnetic and some aren't. Finally, it looks at orbitals from an energy standpoint, which is something that valence bond theory does not do. Valence bond theory talks about where the electrons are. Molecular orbital theory talks about what energies they have, which orbitals get filled first, and things of that nature. Now, done properly, molecular orbital theory is highly steeped in multivariable calculus, but don't worry, we're going to do the math light version of MO theory in Gen Chem. So we are talking once again about what happens when two atoms come together, and when that happens, we can first of all predict the shape of the orbitals that are formed. We can use a molecular orbital diagram to predict which orbitals electrons will be found in, and also we can figure out the bond order and magnetism. So let's start off by talking about the shape of the orbitals, and then we're going to go through and do the rest. So one way that molecular orbital theory is described is the linear combination of atomic orbitals. What the heck does that mean? So what we're going to do is we're going to talk about combining two atomic orbitals, and we're going to do this by using as an example the simplest possible molecule we could possibly make. And so basically we're going to start with a hydrogen atom that has one proton and one electron, and then we're going to start with an H+ ion which has one proton, no electron. So it has an s orbital, but there's nothing in it. So as these come together, the nucleus of the B atom, the one without an electron, is going to be attracted to the electron that hydrogen A has. And so they're going to come together, and now because there's the space, the empty s orbital of hydrogen B, where there's space for an electron, the electron can now move throughout a space that is pretty much the space that it used to have with nucleus A, plus the empty space that was available around nucleus B. So that's what we're talking about when we're talking about combining orbitals. So very much like what valence bond theory says, a molecular orbital is formed when atomic orbitals combine to form a new orbital in which an electron can interact with both nuclei. And that's really what we're trying to do here. We're trying to figure out what orbitals will form. Now, let's talk about linear combinations. So if you think back to when you did algebra, they talked about how if you have two variables, you need to have two equations. So I've thrown something up that has two variables, x and y, and we have two equations with x and y. And in order to find the solutions for these variables, you would basically combine them in two different ways. First, you would add them, and that would give you the solution, in this case, for what x is. And then you would subtract one equation from the other, and that would give us the solution for y. Anytime you have two equations, you can get two solutions by basically combining them in different ways. And that's pretty much what we do with orbitals. You might say, hey, an orbital is just an area in space. How can you add it? But that area in space is defined by a probability function. So you could add the two probability functions, and in this case, let's put them together, and the way we add them is we look at where they overlap, so this area right here, and anywhere where it overlaps, we're going to get extra probability there. And so when we add them, we basically get an area with a high probability density between the two nuclei. Now, of course, as I showed you before, we can also subtract the molecular orbital probability functions to give us a new orbital. So again, let's put them together, let's overlap them, and now in this area where they overlap, Because we're subtracting, that is an area where there's going to be no probability that the electron can be there. So we'll end up with something that looks approximately like this. Now you can see we have here what we call a node, which is we can basically run a plane between those two halves of the orbital, and it's symmetrical about that node. And there's also no connection between one half of the orbital and the other. So what does this mean for electrons that are trying to hold two atoms together? So kind of a quick detour. Let's talk about sigma orbitals and pi orbitals when we're talking about molecular orbital theory. Just like with valence bond theory, sigma and pi orbitals are classified based on their symmetry. So sigma bonds are any bonds that have rotational symmetry around a line through the nuclei. Pi bonds have symmetry through a plane that contains the nuclei. So that is exactly the same way we define them in valence bond theory. So now let's go back, let's look at those orbitals that we were just talking about. And both of these are sigma orbitals. So you can see if we draw a line through both nuclei, those things actually will rotate around it. And of course they look two-dimensional because that's about the best I can do in PowerPoint. But those actually are rotationally symmetrical. But these behave differently. So here's the first orbital, the one that we got by adding those two 1s orbitals together. And you could see that the highest probability density is between the two nuclei. And so a negatively charged electron that's between the two nuclei is going to pull both nuclei towards it and will pull them together. That stabilizes the molecule, and so we call this a bonding orbital. This is a sigma bonding orbital. This is what we call an anti-bonding orbital. So let's think about where the electrons are likely to be. They have to be in one half or the other, and they're probably going to be on the far side of the nucleus. So what is going to happen? This electron is going to pull the nucleus towards it, and it's going to pull it away from the other nucleus. That will destabilize the molecule. It will pull the molecule apart. That's why we call it an anti-bonding orbital. This particular anti-bonding orbital has sigma symmetry, so we call it a sigma star orbital. The star tells us that it is anti-bonding. Okay, so the next thing we were going to do is use a molecular orbital diagram, and I'm always going to abbreviate it as MO here, based on energy levels to predict which orbitals electrons will be found in. So now we need to learn how to draw a molecular orbital diagram. So here's an example of a molecular orbital diagram. Anytime you look at a molecular orbital diagram, the things over here on the sides represent orbitals, which are the atomic orbitals that you're putting together to make molecular orbitals. Those are basically what you start with. And then whatever's in the middle is what you create by putting those orbitals together. You'll notice that there are dashed lines that connect the atomic orbitals to the molecular orbitals, and those basically confine the electrons to basically say the electrons from these atomic orbitals can go into those molecular orbitals. That last part may not make much sense yet because we're working with a very simple molecular orbital diagram, but you will see as we move further on, you may end up with several sets of atomic and molecular orbitals. So let's talk about the steps to building a molecular orbital diagram. The first thing is, think about the atomic orbitals you are going to be combining. And for your information, those are only the valence electrons from each atom. So anything that's considered a core electron, you do not include in your molecular orbital diagram. Next, fill in the electrons that correspond with those atomic orbitals. Again, it's going to be the number of valence electrons in your atom. Second step is to draw in the bonding and anti-bonding molecular orbitals, and we're going to get into that a little more as we go through and draw. The third step is to count up the total number of valence electrons you have and place them in the molecular orbitals following the Aufbau principle. And so basically you're going to treat these molecular orbitals the same way that you did the atomic orbitals when you were doing electron configuration diagrams for elements. So let's start by drawing the atomic orbitals that we're starting with. We have two hydrogen nuclei. Each of those is going to have a 1s orbital. And remember, we have an H2 plus. We're starting with one regular hydrogen atom, and then the other one has no electrons, so we're not going to put any electrons in. And now we're going to draw the bonding and anti-bonding molecular orbitals. As we talked about before, this has a sigma bonding orbital, which is lower energy, and a sigma anti-bonding orbital, which is higher energy. Remember, the lower energy something is, the more stable it is. Now let's place the electrons in the molecular orbitals following the Aufbau principle. So we sum up how many valence electrons we have, which is 1. And we always start at the lowest energy orbital, so we're going to put it in there. And that tells us what our molecular orbitals will look like for H2+. So what does this tell us? First of all, that H2+ has one electron, and that one electron is found in the bonding orbital. That means that that one electron will help to keep nuclei together. It will help stabilize the molecule. Now, of course, we rarely see H2+ in nature, so let's build an MO diagram for something we do see a lot, which is hydrogen gas, H2. So again, we'll start by drawing the atomic orbitals that we begin with, one for each atom. And again, we have two hydrogens. This time there's no positive charge, so that means each one has its normal one electron. Now we draw in the bonding and anti-bonding molecular orbitals, which are the same as before. Now we're going to place the electrons in the MOs following the Aufbau principle. So we have two total valence electrons here. And so the first one goes in the bonding orbital, and we can always put two in an orbital, so the second one also goes in the bonding orbital. What this means is now we have two electrons holding the molecule together instead of just one. So remember, the third thing we were supposed to do is to use our MO diagrams to predict bond order and magnetism. So let's start out by talking about what bond order is. And basically, it's how many net pairs of electrons are stabilizing the molecule. Remember that electrons in bonding orbitals stabilize the molecule, and electrons in anti-bonding orbitals destabilize the molecule. So what we're going to do to calculate bond order is we're going to take the number of electrons in bonding orbitals, and we're going to subtract the number of electrons in anti-bonding orbitals. And we're trying to figure out how many net pairs, because remember, we can fit 2 electrons in every orbital, so let's divide the whole thing by 2. And the higher the bond order you have, the more strongly your molecule is held together. So the stronger the bond will be. So let's go ahead and take this equation and apply it to the molecular orbital diagrams we've already done. So again, our bond order is going to be the number of electrons in bonding orbitals, and we have 1, minus the number of electrons in anti-bonding orbitals. Well, our anti-bonding orbital is empty, so that's 0, divided by 2, and so that's going to give us half. Half a bond. We have half a bond. So obviously that's not a very stable molecule because we don't even have a complete whole bond. Now let's do the same calculation for H2. Here we have 2 electrons in bonding orbitals, and we have no electrons in anti-bonding orbitals, so that equals 1 for our bond order. And if you go ahead and draw an electron dot structure for H2, you'll see that it does have 1 bond, which is one of the great things that molecular orbitals do. They predict exactly how many bonds we should have in our structures. Now let's talk about magnetism, and this works the same as atoms. Basically, if you have all of your electrons paired up, it's diamagnetic. The molecule will not be attracted to a magnet. But if you have unpaired electrons, then the molecule will be attracted to a magnet. So here's hydrogen, and you can see that we only have paired electrons in our molecular orbitals. Okay, so make sure you ignore the atomic orbitals that these came from. We're only looking at the electrons in the molecular orbitals. All right, let's talk about how to create molecular orbitals with p orbitals. So there are 3 p orbitals, the px, py, and pz. But there are only 2 ways you can combine them to create molecular orbitals. So the py and the px are going to behave the same way. They're going to have similar ways of overlapping. It's just that in this case, it's the px that's sticking straight out of the screen at us. So it's basically going to look like the py rotated at 90 degrees. So let's take our two PZs, and you can see the reason the PZ orbitals are different from the others is because they lie along the axis that connects the two nuclei. So we can overlap those orbitals this way, but when you look at the Py orbital, and the same would be true for the Px orbital, when you try and overlap them, you can see that they overlap this way, and so the overlap occurs above and below the nuclei. It does not occur along that line between the nuclei. So let's talk about the molecular orbitals that are actually created with PZ orbitals. So we overlap. Again, this is the area that is overlapped. And when you add your two orbital functions, you're going to get more density in that area that you're overlapping. So you get something that looks like this. This is our bonding orbital. But if you subtract that area where they're overlapped, that means you're going to end up with something that doesn't have electron density in that overlapped area, and you're going to get something that looks like this. Now you can see this is very different from overlapping s orbitals. It does have that sigma symmetry in that you have the symmetry along the line that runs between the two nuclei. But what you'll notice is on either side of our nuclei, there is a lobe where electrons can be, and that lobe does not really represent a stabilizing influence. So these are always higher energy than the sigma orbitals that we get from combining s orbitals. Same with the 2p. Again, you can see why this is an anti-bonding orbital. Most of the electrons are going to end up in the area that's not between the two nuclei, and so that is a destabilizing influence. Okay, so now let's look at creating molecular orbitals with the p sub x and the p sub y orbitals. As we move them together, we get overlaps, this time in two different areas. And so we can do two different things with those overlaps. We can add our probability functions, and we end up with more electron density in the areas of overlap. So basically we're going to get two large areas above and below the nuclei. Or we could subtract those areas of overlap, in which case we're going to get areas with no electron density in the areas of overlap. So then we're going to get something that might look like this. So again, these are pi orbitals. You can see they're not rotationally symmetrical around the line between the two nuclei. And so these have pi symmetry. There's basically a plane of symmetry that cuts between the two nuclei, and the molecular orbitals are symmetrical across that plane. So when we make a molecular orbital diagram that includes p orbitals, even though we have 3 orbitals, there are only 2 types of overlap. One set of p orbitals are going to form sigma orbitals. So you're going to get a sigma and a sigma star, a sigma bonding and a sigma anti-bonding. Then you have 2 p orbitals, the px and the py orbitals, that will overlap and form 2 different sets of pi molecular orbitals. So you're going to have 2 bonding orbitals and 2 anti-bonding orbitals. One of the things I'm going to show you approximate energies of the sigma and pi orbitals for our p valence electrons. But in reality, sometimes the sigma orbitals are lower energy and sometimes the pi orbitals are lower energy. And that really depends on the molecule. You can't really predict by looking at the molecule. You actually have to calculate it. I'm just using the same configuration for all of them. But if you look at the scientific literature, you will see that some molecules have the pi orbitals lower and some molecules have the sigma orbitals lower. Since you can't calculate that, I'm not going to push too hard. You can draw them either way, as long as you put the anti-bonding orbitals higher in energy than the bonding orbitals. So of course, we have to do a couple of examples. So we're going to start with oxygen gas. Let's start by drawing the atomic orbitals for oxygen, 2 oxygens in fact. Our valence shell is 2. We have electrons in the 2s and in the 2p, and we have 6 valence electrons, 2 in the 2s, 4 in the 2p, and that's true not just for one oxygen, but for both oxygens. So there are the atomic orbitals with their electrons. Now we're going to draw on the bonding and the anti-bonding molecular orbitals. And you can see here that we have 2 sets of molecular orbitals. We have two molecular orbitals that we created by putting together two atomic orbitals, both 2s. So we have sigma from the 2s orbital and sigma star, the antibonding orbital, from the 2s orbital. And this is what I was referring to when I said those dashed lines tell you what direction the electrons can go. You can see that there are no dashed lines connecting the 2s to the 2p. So you can't take your 2s electrons and put them in any of the orbitals that we made by combining the 2p. Okay, now let's look at the top. You can see that we have one sigma 2p orbital and two pi 2p orbitals. So remember, the sigma is the one that's created by combining the pz. The pi's are created by combining the two px's and the two py's. And then above those in energy, we have our anti-bonding orbitals, and so we have our pi star and our sigma star from the 2p orbitals. Now let's place our valence electrons in these molecular orbitals. And again, we can count up. We have 6 valence electrons from each oxygen, and therefore we have 12 total valence electrons. So let's go ahead and put them in. So we have 1, 2, 3, 4, and as you look, you can see that we had 4 in our 2s orbitals, and we have 4 in this lower set of molecular orbitals as well. Let's keep going. 5, 6, 7, 8, 9, 10, 11, 12. So this is how the electrons go into our molecular orbital diagram. So let's now talk about what this molecular orbital can tell us. First of all, we can use it to calculate the bond order for oxygen gas. And so remember, this is the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So let's see how many electrons we have that are in anti-bonding orbitals. And you can see here, if you look at the purple electrons, we have 4 electrons in anti-bonding orbitals. The remainder of our 12 electrons, so that's 8, are going to be in bonding orbitals. So our bond order is going to be 8 minus 2 divided by 2, and that's going to be 2. So we should have 2 bonds here. It should be a double bond. And again, go back and draw the electron dot structure for oxygen, and you will see, in fact, it does have 2 bonds. Let's now do a molecular orbital diagram for nitrogen. Start with our atomic orbitals. Again, nitrogen's valence shell is the 2 shell, and we have both 2s and 2p electrons. Nitrogen has 5 valence electrons, 2 in the 2s, 3 in the 2p, and of course the other nitrogen has the same electron configuration. Now we get to draw in our bonding and anti-bonding molecular orbitals. And I again have the same setup that I had before. Now we're going to place the electrons in the molecular orbitals following the Aufbau principle. So remember, we had 5 in each of our nitrogens. That means we have 10 total valence electrons. So let's go ahead and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that is our molecular orbital diagram for nitrogen. Now let's talk about what that MO diagram can tell us. Okay, first of all, what is the bond order for nitrogen? Well, the bond order, again, is the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. So let's identify our electrons in the anti-bonding orbitals, just these 2 in the sigma star 2s. And so we have a bond order of 8 minus 2 divided by 2, and that means we have a bond order of 3. So this should have a triple bond. Again, go draw the electron dot structure. You will see it does in fact have a triple bond. So far we've been looking at connecting molecules that are composed of 2 atoms of the same element. But of course, not all atoms are this way. So what changes if you have different elements? First of all, you're not going to have everything at the same energy level, especially if you have things that are from different valence shells. You know that 1s shell combining with a 2s shell, the 2s shell is higher energy. So your energy levels on s and p orbitals may be different. Basically what you're going to do is you're going to compare the orbitals that you're combining. you're going to find the average energy level, and then make sure that your bonding molecular orbitals are below your average energy level, and the anti-bonding molecular orbitals are going to go above your average energy level. So what we're going to do here is we're going to look at FCl. We're going to start with the atomic orbitals, and we're going to put in our valence shell for fluorine, which is 2s and 2p, and then chlorine, of course, has a valence shell of 3s and 3p, which is higher energy. Let's put in our electrons. Fluorine has 7 valence electrons, so there you go. Chlorine also has 7 valence electrons, so those are what we start with. Now let's draw in the bonding and the anti-bonding molecular orbitals. Let's start with the combinations of the s orbitals. So here is our average energy. You can see I basically drew a line halfway between those two orbitals. So now we're going to draw in the molecular orbitals, and you'll notice that they end up being symmetrical around that average energy. So the bonding orbital is just as far below the average energy as the anti-bonding orbital is above the average energy. Now let's talk about combining our p orbitals. And again, this is the average energy. We're going to have 3 bonding orbitals out of this. You can see they're below the average energy. And then the anti-bonding orbitals will be exactly the same amount above the average energy. Orbitals conserve energy. This is something we haven't really talked about yet, but coming in a few chapters, we're going to talk about conservation of energy and why that's so important. And orbitals conserve their energy as well. So now what we're going to do is we're going to place the electrons in our MOs. And once again, we're going to follow the Aufbau principle. So we have 7 valence electrons from fluorine, 7 from chlorine, 14 total. So let's go ahead and put them in our MOs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, let's go ahead and do our usual thing. What's the bond order for this molecule? Well, we can just go ahead and do the math. Again, let's highlight our anti-bonding electrons, and you can see them here in the blue. So we have 2, 4, 6, 8 bonding electrons. We have 2, 4, 6 anti-bonding electrons. 8 minus 6 divided by 2 equals 1. Now, one of the reasons molecular orbital theory is so important is that it explains why we can get resonance. We have talked in the past about how resonance is basically electrons moving from one site to another within a molecule, but how do they move? Here's a molecule that's famous for its resonance. This is benzene, C6H6. And so it is constantly moving in such a way that we have double bonds shifting around, and basically we end up with 1.5 bonds going all the way around this ring structure. And so you can think about what happens to make this work. First of all, we have our sp2 hybridized orbitals, and those lie in the plane of the ring, but there's also these p orbitals sticking up and down from the plane of the ring, and these end up forming molecular orbitals as they combine. So let's go ahead and look at what a molecular orbital diagram looks like for that. And again, this is not something I would expect you to be able to draw. We really only dabble in binary compounds here, just because those are things that you can just come up with without doing any hard calculations. But you can see here, we start with 6 p orbitals. We end up with 6 molecular orbitals, and they're evenly distributed above and below the average energy line. And you can see that all 6 of our electrons end up in bonding orbitals. That's why this is such a stable molecule. So molecular orbital theory is complex, and it's quite possible you will use it in your future studies. I know it gets used in organic chemistry, it gets used in physical chemistry, and I definitely use molecular orbitals as I teach analytical chemistry. So you will see a lot of it. Basically, it's important because it helps us understand many molecular phenomena. It helps us understand resonance. It helps us understand bond orders. It helps us understand molecular stability and magnetism and so much more. So I hope this was helpful, and I look forward to seeing you again soon.